Model evaluation. A lot of people think building the model is the hard part, but honestly, that's not where most mistakes happen. The real mistakes happen after the model is built, because now you have a result, a prediction, a number, and the question becomes, can you actually trust it? That's what model evaluation is about. Not just measuring performance, but understanding whether the model is genuinely useful. And those are two different things. Let's slow this down. When people first start machine learning, they usually focus on one thing: accuracy. What accuracy did you get? Is the model about 90%? And that sounds reasonable. Higher accuracy should mean better performance, right? Not always, because accuracy can be extremely misleading. Let's imagine you are building a model to detect fraud. Out of 1000 transactions, 990 are normal, 10 are fraudulent. Now imagine your model predicts everything is normal. It completely ignores fraud. But statistically, it still gets 990 correct. That means 99% accuracy. Sounds amazing? But the model is useless. It fails at one thing it was supposed to detect. And this is where beginners get trapped. They trust the metric without understanding the context. That's why evaluation matters, because numbers alone don't tell the full story. Now let's talk about confusion matrices. This is one of the most important tools in classification, not because it's complicated, but because it forces you to look deeper. A confusion matrix breaks prediction into four parts: true positives, true negatives, false positives, and false negatives. Now, suddenly, you're not just looking at accuracy, you're looking at the types of mistakes your model makes. And that matters because different mistakes have different consequences. For example, in spam detection, a false positive might just move an important email to spam, annoyingly but manageable. But in healthcare, a false negative could miss a disease completely. That's serious. So, model evaluation is not just technical, it's contextual. You have to ask, what kind of mistakes can the system afford to make? And that changes everything. Now, let's talk about precision and recall. Precision answers this question: when the model predicts positive, how often is it correct? Recall answers, how many actual positive cases did the model successfully find? These sound similar, but they measure very different things. A model can have high precision, low recall, meaning it is very careful when making positive prediction, but it misses many real cases. Or it can have high recall, low precision, meaning it catches almost everything, but also produces many false alarms. And depending on your application, one may matter more than the other. Again, context matters. Now let's talk about F1 score. F1 score balances precision and recall together, because in real world systems you usually need both. This is why serious AI work is not just train model, get accuracy, done. Real evaluation is deeper. It requires interpretation, judgment, understanding, and that's the human role. Now let's move into regression models. Regression problems predict continuous values, things like price, temperature, risk score. Here, we use different matrices: mean squared error, root mean squared error, R squared. These help measure how far predictions are from reality. But even here, matrices can be misleading because averages hide patterns. Your model might perform well overall, but fail badly on specific groups. Maybe it predicts well for younger people, but poorly for older people. If you look at the average, you miss that imbalance completely. And this becomes very important in AI ethics because unfair systems often hide behind strong overall matrices. This is why evaluation must go beyond performance. You need to understand who the model works for, who it fails for, where the weaknesses are. Otherwise, you build systems that looks intelligent but behave unfairly. Now let's talk about validation. One of the biggest dangers in machine learning is testing your model on data it has already seen because the model will appear better than it really is. That's why we split the data carefully. Training set, validation set, testing set. Each one has a purpose. The goal is simple. Can the model perform well on completely new data? Because real intelligence is not memorization, it's adaptation. And the same applies to models. Now let's connect this into a bigger picture. AI systems today are being used everywhere: healthcare, finance, security, recruitment, education. And every one of those systems depend on evaluation because once a model enters the real world, its mistakes become real. A wrong recommendation, a denied loan, a misdiagnosis. So, model evaluation is not just mathematics, it's responsibility. And this is something people forget. The more powerful AI becomes, the more important evaluation becomes. Because powerful systems amplify errors faster. Now, let's bring this back into thinking self. Because model evaluation teaches a deeper lesson. It teaches you not to trust surface level results, not just everything that looks impressive actually works well. And this applies beyond AI. In business, in media, in life, people love simple matrices, simple scores, simple rankings. But reality is more complicated. Real understanding requires deeper analysis. You have to ask what is being measured, what is being ignored, what assumptions are hidden underneath. That mindset is what separates critical thinkers from passive observers. And in a world increasingly shaped by AI, that difference matters more than ever. So the next time you see higher accuracy, strong matrices, impressive numbers, pause. Ask deeper questions because performance without understanding can still lead to failure, and understanding is still the most important metric